In this video, we are going to talk about the various applications of shift registers. The applications that we are going to be looking into. Again, we are not going to go into any uh, too much detail of any of these applications. It's just we need to understand how shift registers are used to construct delay lines. They are used to construct data format converters, how they are used in data processing, how they can be used to design counters, which is another concept that you are going to be studying or may have already discussed. How we can use shift registers to design pseudo-random pattern generators or pulse extenders, pattern recognizers, and interconnections. So these are all components of electronic circuits, and these are all something that you can design using shift registers, right? So let's start with delay lines. Now, SIPO and PIPO shift registers can be used to delay the digital signals by a definite period of time. And you can understand why that is if you just recall what SISO and PIPO shift registers do. Serial input, serial output shift registers, what they do is they take data serially and then they output it serially. PIPO shift registers take data simultaneously and then they uh, let you take it out parallelly. The point is, before the data comes out and after it goes in, right, that period in between when the data is loaded into a register but it is not taken out yet, that is the part where the register is storing your information, and the output of the data is controlled by the clock pulse. That means as long as you don't apply a clock pulse, the data will not come out, right? So it will just stay within the register as long as a clock pulse is available. What that means is you can decide how long SISO and PIPO shift registers hold your data by controlling the delay of your clock pulse. And that is what it means when we say that these two shift registers can be used to delay the digital signal. So information goes in, but it doesn't come out until you apply the clock pulse. So you can delay the output of the information as your own wish. And that is where these two. And if you just think about it, you can see that neither SIPO or PISO shift registers can do the same thing. Just go back to the operation of the other two registers aside from these and just think about it. Just take a look and try to understand why those two can't be used to delay the signals. See, this can only happen if the input and the output of the data is in the same way, right? So this is for you to decide, and this is very simple. You can just go back, take a look at the operation of either of those aside from these, and then you can see that those can't be used to delay the signal, but these can, right? Okay. Multiple bidirectional shift registers connected in parallel can be used as a stack. Again, stack is something, it's a data structure that you already know about and you know how it works, right? So if you use several bidirectional shift registers which you connect in parallel, you can use them as a stack, right? Again, this is something that you need to just visualize how a stack works. The data goes in from the top. It keeps moving down, down, down when new data is pushed. And if you have to take the data out, you have to pop it out. Again, popping is done from the topmost part of the stack, from the top of the stack. So pushing and popping both are operations that are performed on the top of a stack. So if uh, each individual storage element of your stack was a bidirectional shift register. A bidirectional shift register, what it does is it can move the data from left to right and right to left, which is essentially what you need in a stack because the data either goes down or up, that is, either left or right. Okay, so multiple bidirectional shift registers, if you connect them in parallel, what you have is a stack, right? So both delay lines and stacks you can design using shift registers. Another application of shift registers is that they can serve as very good data format converters, right? And all of that has to do with how they take in data and how they take out the data, right? So for long distance communication, serial data transfer is preferred because in parallel transmission, you need to have as many data lines, as many communication channels as there are bits in your data. And if for long distance communication, having that many lines is very expensive, right? For serial communication, you need only one line. It doesn't matter how many bits you're transferring, all of them will travel through the same line, so it's cost effective. But the same data, if you had to transmit 32 bits of data, for instance, across long distances, you will need to use 32 communication channels. It's very complicated, it's very expensive, right? This means that we need a way to convert parallel to serial data. And what does parallel to serial conversion? PISO registers, right? So very clear cut and direct application of a PSIO register is converting parallel data into serial data, specifically for data transmission purposes, right? It saves a lot of money. All right. In general, however, many microprocessor based systems usually prefer parallel form of data in, right? Data in. For input, they prefer parallel form, which means that the transmitted data needs to be converted into parallel mode using serial to parallel converter. So you are transmitting the data. Because of the cost concerns, you're choosing to transmit the data serially. And that is where PSIO registers come in. But on the receiving end, right, a sender and a receiver. So sender has decided to send the data serially. They have used PISO for converting the data into a serial format. But on the receiving end, whatever is on the receiving end, they prefer to get the data in a parallel. See, parallel data is preferred. You'd like to look at all your bits at the same time rather than waiting to get the bits one at a time. It's very time consuming, right? So the sender would like to send the data parallelly, the receiver would like to receive the data parallelly. But because of the transmission cost, you have to perform conversion in between, right? So the sender sends the parallel data by converting it into a serial form using PSIO register. On the other hand, the inverse operation happens. The receiver would like to convert that serial data into a parallel form, for which you use the opposite of a PISO, which is a SIPO shift register. So again, a very direct and useful application of shift registers is data format conversion, that is from serial to parallel and parallel to serial. All right, data processors, again, another application of shift registers, which we actually hinted at various times during this lecture. When we are performing mathematical operations on the data, when we want to process the data, we mentioned earlier that shift registers are used in calculators, right? So you're supposed to add and subtract and divide and multiply your data. And because it is binary data, it has to be stored for some time temporarily. It has to be stored before the final result becomes available. And for that, you use shift registers, right? So for addition and subtraction, initially shift registers were designed to make it simple to perform addition and subtraction. And even now, since you already know about bidirectional shift registers and you know that shifting a number to the left or right is the same as multiplying or dividing that number. So on top of addition and subtraction, shift registers are very useful for performing multiplication and division as well. So all the data processing tasks, all the basic data processing tasks can be done very beautifully using shift registers. Another application of shift registers are counters. A counter is a digital device, the output of which includes a predefined state based on the clock pulse application. So a counter is essentially something that counts. Okay, so the counter is a digital device. It moves through a specific sequence, right? And after the count is over, it starts from the same sequence again. Okay, counters are basically shift registers with serial outputs connected back to the serial input in order to produce a particular sequence. Now, if you remember, after the discussion of SIPO, PISO, PIPO, and SISO registers, we took a quick recap of different kinds of registers, and we said that there are two additional kinds of shift registers that are that shift the data to the left and shift the data to the right. So there's no output. There's just the output is fed back into the system, and this is what a counter is. That's what counters do. So the output is connected back to the input of a SISO register, and that gives you a counter. So what that happens then is That register would then go from specific sequence of bits, and when that sequence is over, it will start from the beginning. And to illustrate what that means, I want to take the help of two counters designed using shift registers, namely a ring counter and a Johansson counter. So so at this point, it's important to understand that counters is actually a separate topic of your syllabus. So we're not going to go into the details of counters any more than we have to. All I want to do right now is just to show you how counters are designed specifically using shift registers, just to give you the idea of the point of having shift registers in counters. And for that, we're going to be taking a look at these two counters, and that is it. Again, we won't go into the details of counters at this moment because that's a separate topic for you. But let's quickly take a look at both ring counters and Johansson counters, just so that you know how counters work and what they do, and how shift registers fit into the whole picture. So let's first begin with a ring counter. And for example, here we have taken a 3-bit ring counter. Again, you can have as many large ring counter as you want. And the point of having more flip-flops or having more a larger counter is that it will be able to count to a higher number than a 3-bit counter. Okay, so let's take a look at what it means when we say that it counts or whatever. Okay, so this is the basic arrangement of your shift registers. We have 3D flip flops here. We have the clock like we used to. This is a serial in. Technically, this is a serial in, serial out register with two important additions, we can say. First is, this is the output line, right? And you can see that this output line is actually fed back into the register and it becomes the input here. So it moves from here to here, here to here, and here to here. Okay, so this is fed back into it. So this is now a loop. Another distinction is these parallel output lines. So we have tabs here, and you can actually take the data out if you so desire. All right, so let's see how this counter works. Again, everything will be controlled by the application of the clock pulses. Now, say that initially in your register the data is 001. This is your data initially, right? 001. When the next clock pulse arrives, this one, which is going to be at this point, right, at the third flip-flop, this one will go out, but it's not going out of the register. Why? Because it's being fed back into the register again. So the one moves from there to there to there, and it then enters your first flip-flop, right? And this is what's happening here. See, this one went all the way and got to this position. So we get 1 0 0. At the application of the next clock pulse, what happens? This one will move one position to the right. That's how a SISO register works anyway, right? So this one has now moved to this position, and that's why we get this. This 0 will move back here, and that's why we have a 0 here, right? And then after the application of the third clock pulse, what happens is this 1 moves one bit position to the right. This 0 is fed back into the system. This 0 comes here. This 1 goes here. And so you're left with 0, 0, 1. And this is the initial state that we started with. We started with 0, 0, 1. And we have ended up, after 3 clock pulses, we have ended up at 0, 0, 1 again. So now what has happened? On top of returning to the original sequence that we started with, which was 001, we have counted 3 steps, haven't we? So that means that using a 3-bit counter, you are able to count 3 distinct sequences. From starting again to the same thing, again to the starting point, we have 3 clock pulses. So this is the concept of counter. You are able to count, and what you're counting in this case is clock pulses, right? So you're able to count to 3 using a 3-bit ring counter, right? Until you return to the sequence that you started with. So you can use any sequence here. You can try 0 1 0, and when you move after 3 clock pulses, you land at 0 1 0 again, and that's the point of the counter. It goes through a specified sequence of bits before returning to the starting point. So you can take an example of 1 0 0 or 0 1 0 or whatever. You land at the same result after counting 3. And this is essentially what goes on in a Johansson counter as well. The difference between a ring counter and a Johansson counter is that this output line in case of a ring counter was this one, but in this case this is Q dash. That's the only difference, right? So in this case, you're taking whatever bit was coming out of this was being fed back into this. That's why when 1 came out, it got here, and then when 0 came out, it got here, and then 0 came out again, it got here. So whatever bit comes out of the third flip-flop goes back into the first flip-flop. But in case of a Johansson counter, the complement of the bit goes back into the register. And with that, you're able to count to a higher number. In case of a 3-bit ring counter, you could count 3 clock pulses. In case of a Johansson counter, using a 3-bit Johansson counter, you'll be able to count till 6. And let's see how that happens. Okay, so initially, let's begin with 0 0 0. This is my initial state of the counter, all right, or state of the shift register. 0 0 0. 0 is Q0, right? 0 is the output of the third register, but what's fed back into the register is the complement of 0, which is 1. That's why when we count the next clock pulse, the sequence is 1 0 0. Even though this was 0, the complement of this will become the input now, right? And then this 1 goes here, it moves to the next flip-flop. That is why in the next sequence, this 1 comes here. So we get this one is the same as this one, all right? At the application of the next clock pulse, this output is not going to be fed back. The complement of this is going to be fed back into the system. So Q0 is 0, but the input that the first flip-flop gets will be the complement of Q0, which is 1. That is why, even though the output here was 0, the input in the next setup is 1. So this one is the one that is being shifted, because shifting is still going on, right? This is a shift register essentially. So this bit is moved to the next position. This output, the complement of this output is moved into the first flip-flop, and this is shifted to this position. And so far we have counted 2 clock pulses. Then when the third clock pulse arrives, this one is shifted here, this is shifted here, and the final output of the third flip-flop, the complement of this output will be fed back into the first flip-flop. That's why this was 0, and that's why this is 1. All right, and so now we have counted up to 3, and then the fourth clock pulse arrives. And then what happens? This one is moved here. See, shifting is still going on. The shifting will take place because this is a shift register essentially. This bit is shifted to the right, this bit is shifted to the right, and this bit should basically be whatever the output of the third flip-flop is, the complement of that output. The output was 1, so the complement of the output is 0, and this is my input to the first flip-flop now. And then we count the next clock pulse. So now we're counting 5. When we count 5, this bit is shifted to the right, this bit is shifted to the right, and the complement of whatever output I had in the third flip-flop will become the input to the first flip-flop. So complement of 1 is 0, so we get 0. And then we count to 6, right? This counting will go on until you get the starting pattern back. All right, this is what we did when we were doing this. We started with 0 0 1, and we will count until we get 0 0 1 again. So this is what's happening here as well. We are going to keep counting the clocks until we get 0 0 0 back, and which is actually something that happens now. So after 5, when the 6th clock pulse comes, this bit is shifted here, this bit is shifted here, and whatever the complement was of this output, it's hidden here. This was 1. So the complement of this will become the input of the first flip-flop, and so it becomes 0. And now we have 0, 0, 0, which is essentially what we started with. So now we stop counting. And how many have we counted? We have counted 6 clock pulses. We have counted 6 clock pulses before returning to the original pattern, which was 0, 0, 0. So again, this counter, what will it do now? It will start again from 0, 0, 0, and it will do the same thing. It will do 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, again 0, 0, 0. So after every 6 clock pulses, it will return to its original setup, and that way you're using a 3-bit counter to count twice the number of clock pulses. So the setup for both these counters is essentially the same. You're using shift registers, you're using serial shift registers, right? But you're able to count up to 3 in this case, and you count up to 6 in this case. And this is how shift registers are used to design simple counters. Right? So counters do two things. They first they move from a predefined sequence of bits. This is predefined because you see this counter will always go from these states. This counter will always go. So these states are predefined. It will move from these states repeatedly over and over again. This is the first thing that a counter does. The second thing a counter does is it counts. Essentially, that's like the basic thing it should do, right? So it should count. It counts the number of clock pulses. How long does it take it to get back to the original sequence from where it started? That's what it counts. All right. So that's enough about counters. Let's move on to the next application of shift registers, pseudo-random pattern generators. Now again, this is something that you may not have heard of in this context, but generally I think you understand what pseudo-random pattern generators are. So whenever you have any application where you need to generate some sequence of random numbers, you use a pseudo-random pattern generator. Right? Some of the applications of this are computer algorithms, designing of computer algorithms, simulations. For simulations, you use pseudo-random pattern generators. In cryptography, when you have to come up with keys, right? You use pseudo-random pattern generators, and you can actually take a look at it. It's a very interesting concept. The concept of pseudo-random pattern generators. We will limit ourselves to the applications of shift registers in this domain, right? So shift registers can be used to generate pseudo-random patterns, which can be used for testing, among other things. Now, in order to achieve this, what you do is the outputs of a few stages in a shift registers are XORed and connected as input to the first stage, as you can see in this case. Right? What's interesting here is outputs of few stages, not like the counters. In case of counters, what happened was the serial output of the entire shift register was fed back into the register. In this case, in this current application, output of few stages are XORed and they are connected as input to the first stage. So in this example, what they've done is they have connected the outputs of the first, second. So the first one goes into the second one goes into the third one, and then they're taken the output of the third one, added a tap here, XORed this output with the output of the fourth flip-flop. So essentially, output of FF3 and FF4 are XORed. See? And that output is then fed back into the register. And then you have a pseudo-random pattern generator. And you can actually take some time and see that this actually does generate pseudo-random patterns. So start with any initial bit. Just start with any bit you like. Keep shifting it. When you get to this point, take that bit, then take the bit coming out of this flip-flop, you XOR them, feed it back to the system, and then if you repeat the process, and you can actually see that you get a pseudo-random pattern, right? The outputs are going to be coming from this side, right? So you can see So just because you're inputting putting the XORed outputs of some of the flip-flops back into the system doesn't mean you're not taking outputs out, because the point is you need to have some sort of pattern as an output, right? So this is the pattern that will be generated from your complement outputs. All right. Shift registers can also be used to design pulse extenders. Now, pulse extenders are circuits which have longer output pulses when compared to the input pulses. So what they do is they extend pulses. It's like in the name of the application. They are pulse extenders. The output pulse is longer than the input pulse. This a somewhat similar application to a delay circuit, right? So the input goes in delay circuits. What happens is the input goes in, but it doesn't come out for some period of time, and that period of time you can actually decide. So you can extend the length of your clock pulse, and that way you can decide how long the data stays inside a register before it comes out. And pulse extender is a somewhat similar concept. So the input pulse is shorter but the output pulse is longer, and that you can decide using shift registers. It depends on how long you're going to keep the data inside the register. Pattern recognizers is something you can design using shift registers. uh, you've already seen how shift registers are used to design counters. Counters are essentially circuits that go through certain predefined sequence of bits repeatedly. Now, shift registers can be used to detect the occurrence of definite patterns. Right, so not only are they able to generate a certain set of patterns, repeated patterns, they can actually be used to detect the presence of definite bit patterns within an input bit stream. So if you have a constant stream of bits, a very long stream of bits, you can actually detect how many times a certain pattern is repeated within that continuous bit stream. For instance, if you wanted to detect the presence of a certain bit stream, say 0101, so this is the pattern you want to detect. So you have a large continuous input bit stream, and you wanted to see how many times is the pattern 0101 repeated inside that bit stream. You can use a circuit such as this one. This is just for illustrative purposes, right? You can design different pattern recognizers for different kinds of patterns. This one detects 0101 specifically. So what it does is you give this is a shift register, right? We have 4D flip-flops like we normally do. We have the clock pulse goes to every one of these flip-flops, and with the help of this additional circuitry, you can detect the presence of 0101 inside the input bit stream, whatever you feed to this register. All right. So every time that input bit stream contains the bit pattern 0101, the output of the NAND gate becomes low. So you can count the number of times the output of this NAND gate becomes low, and that will give you a count of how many times 0101 occurred in whatever input bit stream you fed into this shift register. So this is how pattern recognizers are generated, designed using shift registers. And same way you can, by deciding which specific outputs to combine, you can see here taps are made at this output, and then all of them are combined with this output and this output to go into the NAND gate. By um, arranging these gates and by selecting which outputs go through which gates, you can have different kinds of pattern recognizers. Alright, so every time your input bit stream will have that specific pattern, the output of this gate will go low, and you can count it, and that will give you a very clear picture of the repetition of that specific pattern that you're looking for. Shift registers are also very useful for the designing of interconnectors. Shift registers of the type SISO and PISO can be effectively used to reduce the number of wires. And number of wires, like we discussed earlier, it's a huge issue. It's a large overhead. So every time you have to connect two components parallelly, you need as many wires as there are bits in the data you're transferring. And both SISO and PISO, because they output serial data. SISO takes in serial input and it gives serial output. PISO takes in parallel input and it gives serial output. The point is, both of them generate serial output, which means they effectively reduce the number of wires you need to output your data, because all of the bits, doesn't matter how large your data is, how many bits your data has, they will all come out on a single serial output line. For example, again, not going to too much details of these components. For example, if you had an electronic circuit where you were working with, suppose, LEDs, right? So in order to drive 16 LEDs from a microcontroller, you would require 16 general input output ports, right? But instead, if you used two shift registers connected in serial, this entire task of driving 16 LEDs could be done using 4 input output pins, right? And now we have reached the end of this video. And just to recap, these are the applications that we took a look at. How shift registers are used to design delay lines, data format converters, data processors, counters, pseudo-random pattern generators, pattern recognizers, pulse extenders, and interconnectors.